so that when we press down either on the mouse key or on a controller, we get a pressed and released message coming through from Blueprint. Let's dive in and see how to do this. Now, we don't want to be doing this trace all the time. We only need to be doing it when we're getting ready to grab an object. We don't want to automatically grab it when we get near it. So to actually grab onto something, we need to use a mouse input, some sort of input. Now, previously, we've done this with events in Blueprint, and we're going to do it again with events. We will see how to do this in C++ soon. But we are going to first do it with events. And what I want to do is set it up so that it could work with the keyboard, it could work with the mouse, or it could work with a controller. So to do this, we need input mapping, something that you see quite often in games. And the way we're going to do this is go to our settings cog, we're going to go to project settings, scroll down to the engine, and then input. Here is where we set up things called action mappings and axis mappings. So what these two concepts are essentially the mappings between your controller analog sticks, and is where to the project settings, scroll down to the engine, and then input. Here is where we set up things called action mappings and axis mappings. So what these two concepts are essentially the mappings between your controller analog sticks or buttons, or perhaps your mouse and your mouse buttons or your keyboard. The actions are discrete things. These are things that you press a button and it just happens. There's a press, there's a release. And the axis mappings are things which are more continuous, such as when you move a mouse slightly, or you slightly tilt a controller, there's a degree to which you can tilt it. You can tilt it not at all, you can tilt it all the way, or anywhere in between. Those are axes. We're not going to deal with axes in this section, because all we're dealing with is an action where we are trying to activate our grabber component. So the way we're going to do this is to unfold our action mapping. So you can see there's already a couple of action mappings here. There's a jump, there's a primary action. This has been set up for us because we're using the first person template, and there is a primary action already here. Now let's unfold that primary action, and you will see that there are two ways to trigger them. Primary action, you can use the left mouse button or the gamepad right trigger. Now, because I want to give you an idea of how we can set up our own action mapping, I'm actually going to hit the delete button next to the primary action, and we're going to create our own. So the first thing to do is click the add button next to action mapping. Then we need to give this action a name. In my case, I'm going to call this grab. And then we need to select a mapping. Now, you can either do this from the drop down, where you can select any of the mappings in here, or you can click on that. keyboard button, which allows you to capture whatever you're doing. So you click on it, it goes yellow, and then you click again, or you use whatever key. If I hit space, you can see it puts in spacebar. If I actually click with my left mouse button, you can see it adds a left mouse button option here. So a little mini challenge for you now is to go ahead and set up this action mapping, add the left mouse button. Maybe if you've got a controller, add in a controller button here too. Okay, welcome back. So I'm going to add in a new action mapping, is this add button. And then what we can do is I don't have my controller hooked up at the moment. So what you can do is click the drop down and we can go to gamepad, and you can look for the gamepad right trigger, for example, and that will set it up so that when you pull the trigger on your gamepad, it's going. So we've set it to our content drawer. We're going to look for our BP player and open it up, because the BP player is the one that has the grabber component, and that's what we're eventually going to want to activate and make it grab something. And the way we can do this is by right-clicking in the blueprint event graph and searching for grab. So now there is an input action events grab event, and this is linked up to whatever keys you have set up. You can change that, and you can potentially create screens in the game which allow your players to change the input mappings as well. And what you've got here is two events, a pressed event and a released event. So I'd like to challenge you to log on that particular action. So add a blueprint. Log for when it's pressed, add it for when it's released, and check that your mappings work. So go into the game, use the particular keys that you've mapped to a grab action, and see if your log messages get printed out. Pause the video and have a go. back. So for pressed, we are going to do a print string, which is not going to say hello, it's going to say grabbed. And then we're going to have a released one as well. Again, a print string, which is going to say released, like so. Now let's go ahead into our dungeon level and hit play. And now if we hit the mouse button, it says grabbed. When I release it, it says released. And you can see that that is working as we would expect. Great stuff. Now we've seen how we can set up action mappings that are remappable and mappable to multiple inputs. I'll see you in the next lecture.
Hello and welcome. In this video, we're going to talk about Unreal Engine's Enhanced Input System. Now, I have the Enhanced Input doc engine 5.1. If you're short on disk space, so I have the 30 strings at different says input project already uses the enhanced this debug console command that we can use if our project is configured to use enhanced input. So back to the two sets of information, the input in the x-axis when I'm moving my mouse left and right, and the y-axis when I'm moving up and down. And if I press W, you can see that this other input action called IA-move is now being triggered, and it's even showing me how many seconds I've been holding that button down. And we can see that it too is a two-dimensional to this thing called an show might do, like jumping or opening a door. It can also be used to indicate user input states, like holding a button that changes a character's walking movement to running. Input actions are separate from raw input. An input action is not concerned with the specific input that triggered it, but does know its current state and can report an input value on up to 3 independent floating point axes. And we saw that when we started showing the debug. We saw that our look and move input actions you were able to character to pick something up, while a walk action might require 2 axes to describe the direction and speed at which the user wants the character to walk. So it's just giving an example of when you'd want to use a one-dimensional versus a two-dimensional text. Input mapping contexts map user inputs to input actions and can be dynamically added, removed, or prioritized for each user. So even though we'll need input actions in this class, door context, so that characters looking through a backpack while standing near a door can still select backpack items. They wouldn't be opening doors. When the character closes the backpack, you remove that select item context, enabling the open door context to take effect. So you'll basically have 2 sets of input mapping contexts, and each can handle what happens when you press a particular button or key, but because these can be prioritized, when both are active at the same time, you'll only have one actually working, and that's the one that will have the higher priority. So this is great for more complicated types of projects where you might have the same button do different things depending on what's going on in the game. It says this ensures that the user's inputs will be interpreted correctly based on the character's situation and prevents the need to program code at the input handling level with awareness of the door and backpack systems. So this is making our code much cleaner and easier to maintain. If we just had a single function to handle, say, pressing the E key, then without the enhanced input system, we would have to go into our code and check the situation for the character. Perhaps check to see if it's close to a door, or check to see if its backpack is open. We may have variables and input host modifier input values. So the modifiers will modify that input first and then hand it off to a trigger. So they use post modifier input values or the output magnitudes of other input actions to determine whether or not an input action should activate. So triggers perform checks to decide whether or not some event or function should be fired off. We have some criteria that triggers can check. It says any input action within an input mapping context can have one or more triggers for each input. For example, taking a photograph might require that the user hold down the left mouse button for a quarter of a second while a separate input action for aiming the camera is active. So we have two different things, right? You have to be aiming the camera and then you have to hold the left mouse button for at least a quarter second before you can trigger some sort of action. In this case, it would likely be taking a photo in the game. Make them. It says input actions are the connection between the system and your project's code. That's the enhanced input system. You can create an input action by right-clicking in the context browser, expanding the input option, and choosing input action. To trigger an input action, you must include it in an input mapping context. So that's another type of asset that we have to create. And add that input mapping context to the local player's enhanced input local player subsystem. So it mentioned these things earlier. Now it's showing how to do it. So it shows how to make an input action, and we can go back into the editor. And in the third person template, under third person, we have three folders. Of course, the character blueprint is in the blueprints folder, but it also has an input folder. And if we double click that, we see IMC default. IMC stands for input mapping context. So this is that input mapping context we were talking about. And then we have an actions folder, and inside of that, here are the three actions that we saw when we were running that debug command. We have IA jump, which stands for input action jump, IA look, and IA move. And of course, we can always create new ones by right-clicking, going to input, and choosing input action. And now we'll have a new input action, and we can double-click it to open it up. And here is where we can set up its defaults. Now, there isn't a whole lot here. I'm going to point out value type here, and it says digital bool, but the drop-down allows us to choose a axis 1D, that's a single float value, axis 2D, two float values like our move and look input actions. They had those X and Y axes, or we can have a three-dimensional value type, a 3D vector. So we know how to create an input action. The documentation says, to make your pawn class respond to a triggered input action, you must add an event to your blueprint graph. So it's talking about how to set this up in Blueprint. Each input action generates an event with its own asset name. For example, to open it up, and here is where we can set up its defaults. Now, there isn't a whole lot here. I'm going to point out value type here, and it says digital bool, but the drop-down allows us to choose a axis 1D, three-dimensional value type, a 3D vector. So we know how to create an input action. The documentation says, to make your pawn class respond to a triggered input action, you must add an event to your blueprint graph. So it's talking about how to set this up in Blueprint. Each input action generates an event with its own asset name. For example, context means this was automatically generated as soon as we created this new input action here. And of course, we can access different folders with the same name. You will see multiple events with that name in this list. You can hover over them with the mouse to reveal their tooltip, which will reveal the action pins and additional input action. But if I go back out one level to this folder and make a new input action and let it simply be called the same name, new input action, well, now if I go back into the event graph and type new input action, I see two of them. That's because two of them exist in my project. I'm going to delete this new called new input action. So we can see that blueprint a axis 2D and save that. Well, now if I go into BP third person character, we have a different event node. This will execute the appropriate pin or pins on each tick based on the state of my action. So these are on a per tick hierarchy with a list of input actions at the top level. So let's take a look at the input mapping context in the third person example project. We can go back out to the input folder, and here's IMC default, an input mapping context. If we double click on it, we see that here's that hierarchy we were talking about. Take a look, we have mappings with 3 different input. So here's the top. This example project has the right thumbstick on a gamepad. So it says under the input action, that has to do with modifying the input using modifiers, and restrictions that it must meet in order to drive the input action is referring to those triggers which determine whether or not we meet some criteria. So for example, we can expand spacebar and we see triggers and modifiers. And both of these have 0 array elements. These are arrays. And you can click plus to add triggers or add modifiers, but the spacebar has neither of those. In other words, if we press the spacebar, the IA jump input action will be triggered. We don't have any really restrictive requirements, and we don't need to modify any raw data or triggering off this input action, but we do have a modifier, and if we expand it, we see that this modifiers array has this single element, and the modifier is called swizzle input axis values. We're going to learn what that means, but if we expand the dropdown, we'll see that the enhanced input system has multiple types of modifiers just built in, and the documentation mentions that you can make your own in the order in which they appear in the list modifier to perform data, and then passes it on to the next modifier, which is called negate. Now you can imagine what negate does. It'll take a positive value and turn it into a negative, or take a negative value and turn it into a positive. So when we press the S key, we're first swizzling it, then the result of that modification is passed to the negate. With X, Y, and Z, we could check or uncheck, but we can add input action cut by clicking on this keyboard icon and context. And of course, new input action can be linked. Let's say we want to press the D key to move right and the A key to move left. Well, we could simply use all of the relevant input actions. We just added our new one to our new input mapping context. For a simple project, you can put all of your actions into a single input mapping context. More complex projects work best with multiple input mapping contexts, since a local player can have more than one active input mapping context at a time. As an example, you can give a character who can swim, walk, and drive vehicles multiple input mapping contexts, one for common actions that are always available and always mapped to the same user inputs, and another one for each individual mode of travel. Developers can then place the vehicle-related input actions into a separate input mapping context, which are added to the local player when entering a vehicle and removed from the local player when exiting the vehicle. So in our case, we know that the template project already has these basic movement input actions to handle jumping, moving, and looking, right? Now, we created another input mapping context, and we may wish these to trigger different gameplay logic, perhaps when opening an inventory menu or doing something else, and our character can still have this default input mapping context, but in some situations we may wish to add this input mapping context so that certain keys will do different things because they're associated with different input actions. And the docs say that doing this helps optimize and prevent bugs by ensuring that inappropriate input actions cannot run. So whenever we have any given one or the other is active at a time. It says, see the sections on modifiers and triggers. Make sure that our input action doesn't get triggered off until we have the actuation threshold of 0.5 seconds. If we move that thumbstick in a shorter period of time, the action won't be triggered off. So this allows us to make sure that that thumbstick is being held at least for 0.5 seconds. We see that this particular run action has a modifier as well. It has a dead zone, and you can set some parameters here. So when moving that thumbstick, here are the thresholds that determine whether or not we even try to trigger this input action. And if we're not moving that thumbstick away from the center enough, well, then nothing will happen. And here's the description. It says, this input mapping context shows an input action for running. This can be activated by multiple inputs, including a gamepad's left thumbstick deflection. Here we're only seeing that gamepad left thumbstick, but we could add other inputs as well. And it says it combines both axes into a single input. So in other words, how far left or right we're moving the thumbstick and how far up and down, those are combined into a single 2D vector. It says that input's raw value will go through a dead zone input modifier. That's the dead zone we just talked about. And the resulting value will be sent to the hold input trigger to drive the run action input action. So the modifier changes the data, right? It'll return 0 if we're not deflecting that thumbstick enough. And then after all modifiers, that data is passed to the trigger, and the trigger will check its own criteria, such as, have we been holding that button long enough? And here we're showing how you can add multiple types of input to a given action and that shortcut key that we discussed. It says there are a large number of input bindings available in the drop-down menu, right? So you can select spacebar or gamepad face button. But to select your input binding more quickly, click the small button to the left of the drop-down and then press the key or button you select. It says this simple input mapping context supports input actions for running and jumping. Now, once you have populated an input mapping context, you can add it to the local player associated with the pawn's player controller. So in any given game, if you're controlling a pawn or a character, which is also a pawn, you have a player controller. You need to access that player controller first to add an input mapping context so that that player can provide input to control the pawn. It says you can achieve this by casting the pawn's controller to a player controller, getting its enhanced input local player subsystem, and adding the input mapping context to it. So again, there's this enhanced input local player subsystem. This is a class that will already exist in the game as long as you have the enhanced input plugin added to your project. And you add the input mapping context to it, providing an integer priority value. And this is because, again, we can have multiple contexts going on at the same time, and the priority determines which one will be active at any given point. It says the enhanced input local player subsystem also supports querying or removing specific input mapping contexts or clearing all input mapping context. Our project we created is a C++ template project. So this is all done in C++, and we're going to find out how that works and how to do it in C++ later on. But if this were a Blueprint project and we wanted to add that input mapping context from Blueprint, we can do that. But as the docs say, we have to access the controller. Now, we could right-click in the event graph and type get player controller. Because this is a character class and not just a pawn class, it has a get player controller node. But we can also get the controller with get controller, and the docs are saying that you can call get controller and cast it to a player controller. So we would say cast to player controller, for example, a valid controller. We can type in. Now, once we have this subsystem, we can then input mapping context. So if we had a variable, we could plug that in, or we can simply hard code it by selecting one from the dropdown. Now, I mentioned in this template project, since it's a C++ project, this IMC default input mapping context, the one with all those different keys already mapped in here, this is already added to this character. That's why we can currently play and run around. That's done in the C++ class for this character, but this is the way to do it in Blueprints. We can add, say, our new input mapping context that we just added, and we can give it a priority, and so on. So getting the enhanced input local player subsystem is how we add input mapping contexts to a given player. So it's a little bit different than the old way of doing it. And the docs say each input mapping context that you add makes it possible to trigger the included input actions, those input actions that were added to that input mapping context, running the appropriate events in the pawn's blueprint graph. You can change the set of input mapping contexts at any time during gameplay. So since we've now added this new input mapping context and associated it with this particular controller, we can now use any actions that we add, such as our new input action. So we've linked up the A and D keys to this action. If we go back, remember we have this event that was created once we made that new input action. And once it's triggered, we can do something such as, say, doing a print string node. If we use a print string node, and we take our action value and plug it in, well, our input action, new input action, is two-dimensional. It's a vector 2D. And if we can't have two running at the same time. But here's where priority comes in. I'm going to shift escape and come back up to our add mapping context and change the priority here to 1. Now that this input mapping context is going to be added with a priority of 1, now we should see that this action value input mapping context because it has. So if you're curious, we can see what that looks like in Begin Play in C++ as well. Now, we'll get into how to do this, but as you can see, we're doing basically the same thing that we did in Blueprint here. We're getting the player controller in C++. There's just a controller variable that we can use and casting it to an A player controller. We'll talk about this more later, but we're also getting the subsystem. This is how to do it in C++. We'll talk about that later as well. And once we get that enhanced input local player subsystem, we're calling add mapping context, just like we're doing here. So this is the same way to do it, and take a look. We're providing the context as an input, in this case, but as soon as we give it a value of 1, now this takes priority, and any actions that we trigger different situations. So we see that input modifiers are preprocessors that alter the raw input values that UE5 receives before sending them to input triggers. So we've seen that already. Modifiers just change the raw input in some way. The enhanced input writing a function in the modifier called modify raw and then returning it. So essentially, you will be able to take the current input value, modify it in some way, creating a custom that IMC example of input modifier usage is two-dimensional directional input using a single input action. That's what we're doing here with IA move. It's a single input action and it's a two-dimensional one. If we go to the actions folder and check out IA move, we see that its value type is axis 2D. So IA move is two axes and adding the appropriate input to the input mapping context. So it's talking about mouse and gamepad thumbsticks. That would be our IA look right here. Remember, IA look takes a mouse X. Player has X, Y, and Z, but the Z doesn't matter here because IA look is two-dimensional. It only has X and Y, and this negate modifier will take that Y value and negate it. Let me show you what happens if we uncheck that and go back and press play. I'm going to click in the viewport and move the mouse up and down. When I move the mouse up, I start looking down. When I move the mouse down, I start looking up. But if I go back to IMC default, to the negate for IA look, and check that Y again, and go back and press play, Then when I move the mouse up, I look up, and when I move the mouse down, the values. And again, we haven't talked about what that means, but we're about to now. It goes on to say enhanced input supports input from one-dimensional sources, such as a keyboard's directional arrows or the popular WASD key configuration. So it's saying that pressing a key is one-dimensional, right? You're either pressing it or you're not pressing it. It says you can achieve this control scheme by applying the correct input modifiers, specifically by using negate to make some keys register as negative and using swizzle input axis values to make some keys register as y-axis instead of the default x-axis. So that's what swizzling is doing. By default, if you have an input action that's two-dimensional, like move, right? Move is value type axis 2D. It's two-dimensional, capable of taking a 0. But when we press the key, the x-axis value will change. It'll be a 1 if we're holding the key down, and 0 if we're not holding the key down. In other words, we can't really change the y value of our IA move's 2D vector. So that's where swizzling comes in. If we expand the swizzle modifier, we have some options: YXZ, ZYX, XZY, YZX, and ZXY. In other words, we're changing the order that raw data will fill in the individual axes. It's changing which axis is populated first. Setting this to YXZ means that when we press the W key, instead of the default behavior, which is to pass that raw data into the x-axis for IA move, we're now going to pass that data in to the y-axis for IA move. In other words, when we press the W key, we're going to use Y for forward and backward movement. We want to swizzle input axis values. 8. That's because, as we mentioned, a single key, when linked up, well, pressing the D key without any modifiers is going to a single move gated. Input action can have a 2D vector that can have any modifiers for that, and when we press A, the X value events. This is really nice because if we want to require our player to hold a button for a short period of time before the action is activated, well, traditionally we'd have to use things like timers or delays, but the enhanced input system just has this behavior built in the form of triggers, and it's automatically taking into account how much time is passing for any given input. So this makes it really easy, and you don't have to go and make those timers or delays. Now, it says there are 3 types of input triggers. Explicit types cause the input to succeed if the input trigger succeeds. So remember, a trigger can be an input to another trigger. Implicit types cause the input to succeed only if the input trigger and all other implicit type input triggers succeed. So you can have multiple implicit types, and all of them have to succeed in order for an implicit trigger to succeed. Think about multiple keys at the same time. Lecture. Now, after processing user input, input triggers can return one of 3 states. None indicates that the input triggers can input trigger by extending the base input trigger class or input trigger timed base, and then we see that this is how you can create your own custom input trigger and how to use it. And we won't be making custom input triggers in this video, but the docs here are showing you that you can. So that's the documentation for the enhanced input system. And so now we see that we have several different pieces and things we need to do in order for enhanced input to work for our project. In this project, I put log axis and squiggles. That's just IntelliSense struggling to keep up, linked to this axis mapping. And we have a callback function. We're passing in the address of a bird move forward. And as you can see, my move forward function is really simple. All we're doing is using UELog to I go over the documentation. I highly recommend you and check that. I have a successful compile, so what I can do is I can now launch the editor. So used to be player input and input learn how to do and put it in a new location. The old way, pick up this action with a particular player, and we say local, have to activate them at runtime during the game. To check options here, we could go to keyboard, choose the tab key or the enter key or the number keys. Without any triggers or modifiers, here's my bird pawn blueprint. And if I go to the event graph, I can use begin play or mapping context to this controller. Contact has an action. We're printing true to the screen. Input value of none and a duration of 0 seconds. And we can use a UE log. Button is pressed and 1 if the button is released, and so on, right? Let's do this the new way. Now, to set up select any input mapping context that define type. So that means a couple things. For one, we're going to want to forward declare it here in the header file. We've already learned why we should forward declare rather than include headers in other header files if we can help that. So up at the top, I'm going to forward declare U input mapping context. So now we can use this type even though its header isn't included. It's now just an incomplete type. Once we actually use it in the CPP file, we'll have to include the header where this is defined. Now I want to be able to set this input mapping context from the bird blueprint. So I'm going to make it a U property, and I have this in a protected section. So I can make it edit anywhere if I'd like to set it from the blueprint in the details panel. And if I did want to access this from the event graph, I could use blueprint read write or blueprint read only. I'm going to make it blueprint read only. Since it's not a private variable but a protected one, we can use that specifier. And I'm also going to place this in a category. We'll place it in the category input. So after adding this variable, I have to remember that this will just be an empty pointer until I give it some value, the mapping context, and the priority equal to the result of a cast. Now, we're casting to get controller. Here in C++, we have direct access to that controller variable. Now, it is possible in the future that they may move this into a private section in the base class where it's declared, in which case we would have to use getController, which is an inherited function that simply returns that controller. So we can be preemptive and use getController just in case they ever make controller private. And Unreal Engine does tend to do that with some inherited variables. It'll move them into private sections, and then in child classes like our bird class, they would be inaccessible and we'd have to replace them with the getter anyway. So anyway, now we have the player controller, right? Noticed that the third casting controller to a player controller. Now this might look a little bit confusing, but really it's only doing one thing. It's creating a local variable just like we did in our bird class, only it's declaring it in the if statement, parentheses, and that just means that this local variable only exists in the scope of the if statement. If I were to, say, go outside the if statement and type player controller and try to call a function on it, well, it doesn't exist anymore. It goes out of scope as soon as this if statement. Now, begin play. We could type player controller down here, and we can access functions on it because we created it outside the scope of the if. To make this a little bit more like the template project, we could move this line here into the if to player controller. We need here inside this second if statement. If we tried to use it outside that second if statement, say to try to call it's no longer needed, well then we can do other things in begin play and have 1 pointer's worth of memory freed up for the rest of the function. But nonetheless, all that's happening here is a new local variable of this pointer type is being created, and it's U function get subsystem. This is a template function which requires you to specify the type of subsystem. Subsystems this type with the enhanced input plugin active with the player takes care of local player subsystem. That's a pointer. We'll call it copy this type and we'll go straight to the engine docs. In fact, I can just type into Google UE5 with this type, and the first thing that pops up are the Unreal Engine docs for this type. And we can see that not only is this in the enhanced input subsystems header file, so we can copy that, but it's also in the module enhanced input. Now, I know that we have this plugin active on our project, but to access these header files in C++, this module needs to be added to our build file. So we'll take care of those things. First, we're going to comment out this line, and if we go up to the top and we try to include enhanced input subsystems.h, we get an error here. We can't open that file. That's because, again, this is in that module called enhanced input. We need to add that module to our project's build file. So again, let's comment that out. We don't want any errors there. And in our project, we have our build.cs. Now, my project is called slash, so the build file is slash.build.cs, and here are all the modules being used in it. Now, you don't have to understand C#, that's what language this CS file is in. All you have to know is that when you build your project, these modules are added to the project by default because we're specifying them here. That's why we can access engine classes and header files that exist in these modules, because the build file determines which modules to include. You see, Unreal Engine is a very large engine, and it's made up of a whole bunch of different modules. You can expand the folders here under Engine to see a whole bunch of modules. Here's the plugins folder. All the plugins are modules. And the way to include those header files is to include the modules here in the build file. We want to include enhanced input, so we're going to add a comma to this list and type in quotes enhanced input to include that module. Now, let's go ahead and compile after adding enhanced input to the public dependency module names. And to compile from Visual Studio, because I have live coding enabled, I'm going to close the editor first and then compile my Visual Studio project. We have a successful compile, and with enhanced input added, we should be able to go back to bird. .cpp. For now, we can uncomment enhanced input local player subsystem and see that this type is recognized. We successfully included enhanced input subsystems.h, and now we can create a pointer of this type. So I know that was a lot of work just to create a pointer of this type, but now we have access to the enhanced input module on the C++ side, and now we can use those classes. So looking back at the third-person template project, we see that we initialize subsystem by getting the local player and calling get subsystem, specifying this type in its template and passing in the local player. So we'll do that here. We'll set subsystem equal to local player, and we'll call the static function get subsystem, and in its angle brackets, we'll pass in enhanced input local player subsystem, and in parentheses we need to pass in the local player, which we can get from player controller, and the function is get local player. So we'll add that semicolon there, and now we have the subsystem. And we know that we should check pointers before we use them, so we can say if subsystem. And again, if we want to use this trick where we declare this local variable in the if statement, therefore it will only exist in the scope of this if statement, well, we could do what the third-person template project does and declare and initialize this variable all inside of the if statement here, like this. Now you might be wondering, how does the if project local variable in the if statement there, and we know that we should check pointers passing in the local player. By getting the U local and the mechanics of how the language, all that work just to get the enhanced input local players are optional. There's a default, we'll just pass in 0, just like we did here in the blueprint. Here we're hard input category. Here's our variable bird mapping context. It's set to none. We never actually initialize that pointer, but we can set it because it's edit anywhere. So we can select IMC bird context. So now we'll know that once the game starts, we've set this to a valid value, and this pointer, bird mapping context, has a valid value because we set it in the blueprint. So all that work just to get the same effect that can be linked to IA type U input action. So U input action, it's going to be a pointer, and we can call this move action. Now, this is just an empty pointer, right? Just like bird mapping context. So we want to set our move action to the input action asset that we created in the editor. So we're going to make this edit anywhere as well. We'll go ahead and make it blueprint read only and put it in category input also. So now that we have a uInputAction variable, we can use it to link up a C++ function, which means we'll need a function to call. Again, in Blueprint, we didn't have to make a function because this event was created for us as soon as we made that input action. But in C++, we need to make our own function. So we can make a function. It's going to be void, and we can call it move. Now, in the old way, we used a float called value. The new way is a little bit different. The new way takes a different type of input. And we can see that by, again, looking at the third-person template project. It has a move function as well. It's right here. And look at its input type, input action value. This is a struct that contains information about an input action. This makes it much more versatile because input actions can hold booleans like our IA move that we created, but it can also hold two-dimensional vectors, three-dimensional vectors, or even one-dimensional vectors. And so this way, if we make a callback to link up to an input action, we only have one function signature that we need to worry about, one that takes this input action value, and it's passed in by const reference. So we're going to use that as the input parameter for our move function. So it'll be a const reference of type input action value. There's the reference, and it's called value. And we can make a function definition. And now we have a function. So in Blueprint, we had an event, but in C++, we're making a function. Now at this point, let's go ahead and compile.
Stop taking meeting notes and let ClickUp AI Note Taker do it for you. It allows you to focus on your meetings, not your
solution, which means I'm going to close out the editor, clicking Save Selected, and here in Visual Studio, I'm going to go ahead and hit Control-Shift-U Input Mapping Context. So we'll forward declare U input action here. So that takes care of that type. But we also have some issues with line 35, which is now 36 because we added that forward declaration up there, and that's referring to the compiler not knowing about this type. Now this is a struct, and we can't forward declare something that's not a pointer. This is not a pointer. But structs in Unreal Engine are typically small, and it's generally safe to include their headers here in the header file. In fact, look at the template project for the third-person template. Scroll up to the top of the characters.h file, and there's the input action value header. So we can see that even in this example, Epic was okay with including this header here in the characters H file. Since we now know that this is the include for that struct type, we can copy it and we example, Epic was okay with including this header here in the characters H file. Since we now know that this is the include for that struct type, we can copy it and we can add that include here to the top of bird.h, but we have to be careful. If we're including a header here, it has to be above the generated.h. Remember, that has to be the last include in the header file. So now let's go ahead and try to compile. And now we see that we compile successfully. So for these pointers, we can forward declare, but for this struct, f input action value, we need to include the header file because we're not forward declaring. We can't forward declare if it's not a pointer. So now that we have this move function, we want to make sure that it's working, right? And in the old way, we just had a value of float type, and we were able to print that to the screen. But now we have an f input action value. So how do we get the input actions value from this struct? Well, we can take that value, and being a struct, not a pointer, we can use the dot operator. And f input action value has a get function, and this is a template function because, well, this system was made versatile to handle multiple types of inputs. We can use bool here. If our input action used a 2D vector, we could use f vector 2D. Or if it used a three-dimensional vector, we could use f vector. But in this case, we know that our IA move has the bool type, so we're going to use bool. So by calling value.get, specifying the type bool, we can get this input action's current value. And we can store this in a local variable. We can make a const bool called current value, for example, and we can initialize it. And we can print to UE log if this value is true. Let's just say if current value, then we'll use a UE log. We'll say UE log temp warning. And for the text, we'll say IA move triggered. So now we have a function that we wish to bind to our IA_move input action. The only thing that's left is to actually do that binding. And we do that in setUpPlayerInputComponent, just like in the old way of doing things. In the old way of doing things, we took the player input component, which gets passed into this when this function is called. But component we're casting the want to continue the game. We want the game to crash so we can come back and see what's wrong. And of course they use that trick again where they declare this pointer in the if statement and initialize it by casting player input component to enhanced input component. Now that means we need the header for this, and I can just scroll up because here in the third person template example we have enhanced input component here, so I can copy that include, and up here I can paste in enhanced input component. So we need to cast our player input component to an enhanced input component. And since we're no longer using the old system, I can either remove this line or just comment it out and move it out of the way. So let's cast player input component to an enhanced input component. So we can say if, and we can declare the variable here, enhanced input component. We can call it enhanced input component. And we can initialize it, and we'll use a cast. But I'd like to use cast checked. I think that's a good idea. We'll crash the game if the cast fails. Now we're casting to enhanced input component, and the value we're casting is simply the player input component we already have access to in this function as an input parameter. So we'll pass that in, and now our if statement has this local variable inside of it. Now in the old way, we would call bind access on the player input component, but the enhanced input component has its own function that we can use to link up our move function to our move action. Remember, we created a variable move action here. It's a input action, right? So here's how it's done. We take our enhanced input component pointer and we call bind action on it. In the old way, we had axis and action mappings, and in the new way, there's only bind action. Now the first input to bind action has to be a input action. We have that, it's called move action. And we still need to remember to set this in the blueprint. So we'll pass in move action, and we're still getting that red squiggle, so there's something that we need here. And if we look at the third person template project, we see that it includes component/input component.h. If I go ahead and include that here at the top, we'll put it right there, then we can now see the next input parameters, and the next one we see is eTriggerEvent. Now this is an enum, we can tell because it's prefixed by E. And if we type eTriggerEvent with the double colons, we have all the options. These are all states that our action can be in. It can be canceled, completed, none, ongoing, started, or triggered. Now we want our move function to be called when this action is triggered, so we're going to choose triggered. And the next input is just a object called object. Much like we did in bind access, we can use this as this is the object we're concerned with calling a function on. And next, we see that we can pass in a function name. We can also pass in the address of a function. That's what these T method pointers are. They're wrappers for function addresses. So we can use the address of operator, and we can use our new move function, aBirdMove. We need to use the class name and the scope resolution operator that fully qualifies that function name. So this function is going to bind our move callback to our move action. So this wasn't something we needed to do in Blueprint because that auto-generated event IA_move in Blueprints is just automatically linked. But if we want our own custom C++ function linked up to our input action, we have to do it this way in setUpPlayerInputComponent. So that's the last piece of the puzzle. We should be able to compile and test this out. So I have my editor closed. I'm going to go ahead and compile, and we have a successful compile. So now I can open up my project, and I'll go ahead and open my blueprint. And we see that nothing's linked up here, so none of this matters anymore. I'm going to go ahead and remove all those nodes. And again, we have to remember to select BP Bird Self. And we have our bird mapping context. We already set that. And we have our move action. This is an input action. And we can choose our IA move. That way, that pointer in C++ will be valid. And it needs to be valid because we're calling bind action, specifying that move action variable. Then we'll use a UE log. We'll say UE log temp. We do that in setup template project. If we go to setup player input component, we see that that's exactly what we're doing. We're casting the player input component to the enhanced input component. Now it's using cast checked, which is like cast, but it also asserts that the cast will succeed. If the cast fails, cast checked can actually crash the game for us. Now, you might think that intentionally crashing the game is a bad idea, but in this case, it's good because if our cast to this enhanced input component type fails, we don't want to continue the game. We want the game to crash so we can come back and see what's wrong. And of course, they use that trick again where they declare this pointer in the if statement and initialize it by casting player input component to enhanced input component. Now that means we need the header for this, and I can just scroll up because here in the third person template example, we have enhanced input component here, so I can copy that include. And up here, I can paste in enhanced input component. So we need to cast our player input component to an enhanced input component. And since we're no longer using the old system, I can either remove this line or just comment it out and move it out of the way. So let's cast player input component to an enhanced input component. So we can say if, and we can declare the variable here, enhanced input component. We can call it enhanced input component. And we can initialize it, and we'll use a cast. But I'd like to use cast checked. I think that's a good idea. We'll crash the game if the cast fails. Now we're casting to enhanced input component, and the value we're casting is simply the player input component we already have access to in this function as an input parameter. So we'll pass that in, and now our if statement has this local variable inside of it. Now in the old way, we would call bind access on the player input component. But the so let's casting player input component to enhanced input component here, so I can copy that include. Here, I can paste in enhanced input component. So we need to cast our player input component to an enhanced input component. And since we're no longer using the old system, I can either remove this line or just comment it out and move it out of the way. So let's cast player input component to an enhanced input component. So we can say if, and we can declare the variable here, enhanced input component. We can call it enhanced input component. Access on the player input component, but in the new way, there's only bind action. Now the first input to bind action has to be a input action. We have that, it's called move action. And we still need to remember to set this in the blueprint. So we'll pass in move action, and we're still getting that red squiggle, so there's something that we need here. And if we look at the third-person template project, we see that it includes component/input component.h. If I go ahead and include that here at the top, we'll put it right there. Then we can now see the next input parameters, and the next one we see is eTriggerEvent. Now this is an enum, we can tell because it's prefixed by E. And if we type eTriggerEvent with the double colons, we have all the options. These are all states that our action can be in. It can be canceled, completed, none, ongoing, started, or triggered. Now we want our move function to be called when this action is triggered, so we're going to choose triggered. And the next input is just a U object called object. Much like we did in bind access, we can use this as this is the object we're concerned with calling a function on. And next, we see that we can pass in a function name. We can also pass in the address of a function. That's what these T method pointers are. They're wrapped on our own those nodes. And if everything works, we should see our UE log printed to the screen. That move action variable, and this line will link up our move function to it. So, if everything works, we should see our UE log printed to the screen. And we call bind action on it, like this. Now, you might be wondering, how does the if statement succeed or fail? Well, this comes down to C++ valid pointer, and it's biased. We can do this bird mapping context. This is a U input mapping context. We can pass that in, and because it's edited, an input action about an function definition, and now we have a zoomed, means it doesn't really know line pointer. This is scroll up to top of a get function, and this is a template function because, well, this system was made versatile to handle multiple types of inputs. We can use bool here. If our input action used a 2D vector, we could use f vector 2D. Or if it used a three-dimensional vector, we could use f vector. But in this case, we know that our IA move has the bool type, so we're going to use bool. So by calling value.get, specifying the type bool, we can get this input action's current value. And we can store this in a local variable. We can make a const bool called current value, for example, and we can initialize it. And we can print to UE log if this value is true. Let's just say if current value, then we'll use a UE log. We'll say UE log temp warning. And for the text, we'll say IA move triggered. So now we have a function that we wish to bind to our IA move input action. The only thing that's left is to actually do that binding. And we do that in setup player input component, just like in the old way of doing things. In the old way of doing things, we took the player input component So we'll forward construct, and we can't forward declare something that's not a pointer. This is not a pointer. And there's the input act for that. And we were able to print in what the third person template project does and declare and initialize this variable all inside of the if statement here. And initializing a new pointer. So what does this whole expression return for the if statement? Well, when you declare a new variable such as a pointer, then the return value of the entire expression whole bunch of different modules. As well, we're using this class, and we need to include the header file where this is defined. Otherwise, the U enhanced inputs associated with the player. It's no longer needed. Third pawn, we created the player controller value be hard code at work just to get for that input action called IA move. C++ input action, and now we have a function. So in Blueprint, we had print, but so we can use the address of operator and plug. And I've linked the W single key, the W key linked to move for basic. And we're going to get it. Value type is bool, twant, true or false, stores a variable of type input action. And so here in can use this as the
Hello and welcome. In this lecture we're going to be looking at how we can create new nodes in Blueprint from our C++, so that essentially we can be calling C++ functionality from within Blueprint. Let's dive in and see how it's done. Now it's all well that I can use Blueprint to call to Blueprint nodes, but I actually want to activate our grabber from this piece of Blueprint here, not print out some strings. So how do I go about doing that? Well, fortunately, we can quite easily expose a function from a C++ class into Blueprint. And the way we do this is as follows. So we're going to go and create a new public function. So I'm going to go to my public section just under the tick component. And here I'm going to create a new function with a void return type called release. So we're going to do grab later on, but we're just going to call the release function for now. How do I make this available in Blueprint? Well, I need to make it a U function. So you've got U properties for variables. U function is kind of the equivalent for making a function basically visible in the land of Blueprint. But we don't stop there. Just like with the U property, we have to make it edit anywhere. Here, with the U function, we have to make it Blueprint callable. And that, as the name suggests, means that this function now becomes a node that Blueprint has access to. So let's go over to the grabber CPP and create an implementation for this. It's going to be void return type. It's going to be a U grabber : release, no parameters, and we'll put a function body, which I'm going to stick a ulog in, and I'm going to give the message be released grabber, like so, and then we can compile, and back in our BP player, I'm going to delete the print string node, and I'm going to drag off of released here, and I'm going to search for delete, and then we can compile.
like so, and then we can compile, and back in our BP player, I'm going to delete the print string node, and I'm going to drag off of released here, and I'm going to search for release as a function in here. Now let's go and have a little bit of a look around. Nothing's showing up at the moment because I need to do this on the grabber. So let's take the grabber component, drag it into the event graph to create a grabber variable, then drag off of this and search for release. Now you notice nothing's coming up in this case either, and that's because we've used live coding, and sometimes things that are compiled in live coding do not show up in the editor. What we have to do is close down the editor, close down the live coding window, and then in Visual Studio Code, hit Build, wait for that to Editor Player, and now dragging off the grab, and indeed C++ things into the dungeon, and we're going to hit play. And now, if I were to grab and then release and dock it to the layout, then hit play again. And now when we grab and then we release, you can see there's a brief message there doing this hit gargoyle state, looking, execute blueprint. You're going to do it the same way as I just did the release function. But when you create the body of the grab function, instead of just printing anything, let's move that sweeping code and the if statement and all the prep variables from tick, so that it's not doing it every single time we tick, to just when we call that grab function, when we press our mouse button down or press a trigger on our controller. So then recompile and check the logs to make sure that indeed that's only happening when you press the button. Pause the video. video and have a go. Release, I'm going to create a new U function and void U, and I'm going to move all of this code from tick component. Let's go all the way down and paste it into grab instead, where it should be just fine. Now let's see if live coding will bring about the player, delete our print string, and let's add function. Okay, so this time pin. Go over to our dungeon, hit play, click into the left button that says release right, sort of architecture in place, this gargoyle. Next we need to deal with Hello and welcome. In this lecture we're going to be adding a new component to our BP player, the physics handle, and we're going to be learning how we can get a pointer to it in our grabber component. We're also going to look at how we can protect ourselves from accidentally crashing the engine. Let's dive in and see how. Now, in order to grab hold of an object, we need to interact with the physics system, and there is actually a component that we can use called the physics handle, which allows us to grab physical objects and tell them where we want to be in the world, but do it in such a way that it acknowledges physical constraints, so it doesn't pass through walls, and it kind of looks like the object is on a spring rather than rigidly following a specific point that we tell it to go to. So we're going to use this physics handle component. We're going to go and add it to our player BP along with the grabber. So let's go to the add button under the components pane and look for physics handle and add it in. And you can see that it's an actor component, not a scene component, because it goes down in the lower section. So it doesn't actually, we're going to go and add it to our player BP along with the grabber. So let's go to the add button under the components pane and look for physics handle and add it in. And you can see that it's an actor component, not a scene component, because it goes down in the lower section. So it doesn't actually have a physical transform of its own. What we do with the physics handle is we tell it the object to grab, and then we tell it where we want it to put the object that we've grabbed. If you go over to the documentation, you can see this in the functions that are available. You scroll down to the functions section, you can see that there is a release component and a grab component at location function. There's also a set target location and rotation. This is where it wants to try and put the object, but obviously it will respect any physical constraints in doing so, and it will do it in a smooth way as if it were on a spring. Now, we're not going to use these functions just yet, but we do need to find a way of getting hold of this component in our grabber component. So how do we do that? Well, let's go over to our grabber CPP and have a look in begin play and try and get hold of it. Now, there's a function on any actor which allows us to find a component by its type. But what is the type of the physics handle? Well, it is a U physics handle component. Now, to get hold of this type, we need to use an include, and you can see the include in the documentation is physics engine / physics handle component. So let's copy that, go over to our grabber CPP and add it in under our draw debug helpers. Then what we're going to do is we're going to do a get owner to get hold of our owning actor pointer, then do an arrow and call find component by class. Now, this function is a special kind of function called a template function in C++, and this means that you can pass it some parameters that actually get evaluated when you compile. And the way you do this is using angle brackets like this. So you use an angle bracket after the function and you give it the type that you want it to find, which in our case is the U physics handle component, like so, and then you close the angle brackets. But because it's a function, you do need to call it using regular parentheses as well, so then you put the second set of parentheses after this. So you can see that these compile time arguments are passed in using the angle brackets, and then the runtime ones are passed in using the parentheses. Now, like a regular function, this will have a return value. And in this case, the return value is going to be whatever type we've passed in here, but as a pointer. So we can take a uPhysicsHandle component pointer and create a variable for that, which we're going to call the PhysicsHandle, and set it equal to this getOwnerFindComponent by class. Now let's remember a semicolon at the end of this line, and that is everything required in order for us to get hold of another component on our same actor. Now remember that I told you that pointers can be dangerous because sometimes they can be null, and that can lead to a crash. So imagine we'd forgotten to put a PhysicsHandle component on our actor, or we've put a grabber on a new actor and we haven't hooked it up with a PhysicsHandle component yet. If this is the case, then the PhysicsHandle pointer is going to be a null pointer. And if we try to use the arrow operator or dereferencing operator on that pointer, it will crash our engine, and it can be sometimes really hard to see what that crash looks like. So I'm just going to go ahead and actually cause this crash just to show you, and you might be able to recognize it if it happens to you in the future. I'm going to reassign our PhysicsHandle pointer equal to the null pointer special keyword. It's all null PTR. That's how you spell null pointer in C++. Then you put a semicolon at the end. And then what we're going to do is we're going to do PhysicsHandle arrow get name, like so. And if we go ahead and compile using live coding, and when that's finished compiling, we're going to go ahead and make sure first of all that we save anything that we've got here going on in our BP player, because I'm about to crash the engine. And if I go ahead and hit play, this is the result that we get, a crash reporter. And you may be tempted to think when you see this that something's gone wrong with Unreal, but it's actually your code that's at fault here. You can see that in this crash report, the first line says that the issue is coming from uGrabber : begin play, and it's actually giving us the line number as well, which is line 28. So you can see that at this point on line 28, when we dereferenced that pointer in order to call a function on it, we actually committed a grave error in not checking first whether that pointer was null. So that's what we need to do, and we do that with an if statement. We basically say if PhysicsHandle is not equal to null pointer, then we can go ahead and call stuff on that PhysicsHandle. So we can put the PhysicsHandle getName inside of this if statement, and that protects us because that code, that dereferencing code, won't be executed in the case where we have a null pointer. So I'm going to go ahead and remove line 27 now, where we are setting it to a null pointer, and I'm going to challenge you to print the component name for yourself. So only print if we have the actual component, basically we don't have a null pointer, and use an else to warn if we didn't manage to get hold of that component, and try removing the component to check. Pause the video and have a go. Okay, welcome back. So we're going to create a new U component to check. Pause the video and have. everybody, welcome back. So we're going to create a new ulog message here, and we're going to say got physics handle colon %s, and we've got this physics handle name, which I'm just going to cut and paste as the second argument, or the fourth argument into the ulog, and I'm going to put a star because it is a string. Now let's add an else statement under our if statement, and in here we're going to put another ulog, which is going to be, this time instead of a display, we're going to put a warning type message, so it's going to come up in yellow, and we're going to say no physics handle found. Once that's launched, let's go. The name is funny enough, physics handle. Delete that physics handle to our BP player, and we should see the log message got physics handle, which the name to our BP. Go ahead, that no physics handle back because we are within a component, and we've learned how to deal with. Hello and welcome. In this lecture we're going to be learning to draw debug spheres in our scene so that we can visualize different F-vector locations in space. Let's dive in and see how this works. So very soon we're going to want to call our grab component at location with a rotation. For this we're going to need to know a couple of things. Which component we're trying to grab, the location, the rotation, in this case the bone name we can happily ignore, but we do need to know these other things. So when it comes to the rotation, this is pretty straightforward because we can just take the rotation of our component. When it comes to the component, that's also quite straightforward. All we have to do is take the component we collide with when we're doing our sphere trace. Now the location on the other hand is a little bit more tricky because we don't just want to take the location of the actual component, because I might be looking at it here, I might be expecting to grab it by its head, but if you see, the root of this object is actually down near the base. So it can lead to results that are a bit strange. I grab it up near the top, near the wings, and it will then move the gargoyle up and float too high. So it doesn't feel right if you do it that way. I've tried and it's just a bit odd. So what we're going to do is we want to find where we hit this gargoyle when we do our sphere trace. If we go over to our grab a CPP, there's actually a couple of options in our hit result for getting some vectors of location. So if you do hit result dot and then hit a control space, you can see a bunch of different things in here. You can see that one of them is the component that we've hit. We will be using that later on. There is an impact point. That could potentially be the interesting one. There's also a location. So to figure out whether it's the impact point or the location that I want, ideally we'd have some way to visualize this in the world, visualize the point that we're trying to see. And fortunately there is. In the same include file that we found our drawing a debug line, there is a draw debug component that we've hit. We will be using that later on. There is an impact point that could potentially be the interesting one. There's also a location. So to figure out whether it's the impact point or the location that I want, ideally we'd have some way to visualize this in the world, visualize the point that we are trying to see. And fortunately there is. In the same include file that we found our drawing a debug line, there is a draw debug sphere function as well, and it has a lot of the same parameters. You need the world as the first parameter, the center of the sphere, the radius is actually draw it, then there's a color, and then whether it, and initially I'm just going to use it to draw a sphere at the end point of our sweep. So we're going to call draw debug sphere. We don't have to include anything new because we've already got draw debug line in here. Get world's going to be the first argument, then the center of this sphere, which is going to be the end vector. The radius, I'm going to give it 10 centimeters radius. I'm going to give it 10 segments as well. And then I'm going to have an F color. This time let's give it something different. F color colon colon, maybe a blue sphere this time. Persistent lines, I do want this to be true because we call grab once, not every tick. So I'm going to set this to true. Then the lifetime, I'm going to set the sphere to last for 5 seconds. And then the rest is less important. I'm going to put a semicolon at the end of the line and recompile. If we go ahead and hit play after it's finished compiling, and we'll move back a little bit from the gargoyle, and I'm going to left click, and you can see the sphere appearing 4 meters in front of where I'm looking. Now I thought it would persist for 5 seconds, but actually what I need to put in here is not that persist is true, because that basically ignores the lifetime entirely and just keeps them around forever. So if we put in false and then the time of 5 seconds, so I just made a mistake there, which is easy to do and easy to misinterpret documentation, and then we go ahead and hit play in our game, and if we create one of those spheres, after 5 seconds it disappears again, so it won't be cluttering our world for too long. So I'd like to challenge you to figure out which location we need from our hit result. Draw a debug sphere for each of them, the hit result.location and the hit result.impact point, and use different F colors to display it and make it clear which one is which. And what's the difference? Which one do we think we might need? Pause. the video and have a go. Okay, welcome back. Let's go back into the code and go down into our if statement where we've got a hit marked out, so we will have some sort of hit result. And just before we get hold of the actor, what I'm going to do is draw debug sphere using get world, and the first location we're going to draw is the hit result dot location. Going to go for 10 radius, 10 segments, F color, colon, green this time, and persistent lines is going to be false, and the lifetime, let's make it 5 seconds. And then let's copy this line because we want almost exactly the same thing, except we want to change out hit result dot location for hit result dot impact point. And the color, maybe we'll switch that out to be red, so that we know the difference between the two, green and red. Let's compile and head over into the editor. Let's hit play. And you see that when I don't actually hit anything, I just get this blue sphere. And if I go up to the gargoyle, look at the gargoyle and try and hit it. Okay, we've got two very different points here. The green one is quite far away from the gargoyle. The red one is much closer. So what's going on here? Well, if we look at the hit result documentation and come down and have a look at what location is meant to be, you can see a discussion here that location in world space where the moving shape would end up against the impacted object if there is a hit. And if I eject and pause for a second to see what these points actually look like, you can see that green one does indeed match that description. We have a 1 meter radius sphere that we are projecting or sweeping towards this gargoyle, and it would hit the gargoyle as soon as it gets to this green point here, because that's about a meter radius around it. Whereas the impact point tells us where that sphere hits the gargoyle. Now that is much more likely to be where we want to grab it, because it's actually on the gargoyle. If I grabbed it over here, the gargoyle would rotate and spin around some point randomly in midair and not look like we're grabbing it at all. Whereas around this red point, it looks like I've just grabbed it by the wingtip, and that would look natural. Great stuff. So in this lecture, we have learned a little bit more about what's available from a hit result, and we've learned how to draw some more debug objects in our scene. I'll see you in the next lecture. Hello and welcome. In this lecture, we're going to be setting up our grabber so that we can actually get hold of our gargoyle statue and take it around with us in front of us. Let's dive in and see how we do this. So it's time for us to start calling this grab component at location with rotation. Now, as I said before, there's actually two parts to this. We need to grab the component, and then later we need to set its target location and rotation as well, so that it moves around. So first things first, in our grab function, we're going to need to get hold of a pointer to our physics handle. So I'm going to copy the line from begin play, and I'm going to go over into the grabber. I'm going to put it in here, and to protect ourselves from this being null, well, what should happen? Well, actually there's nothing that we want to do if we don't have a physics handle. We can't grab anything. So we could put the whole body of this grab function into an if statement, but that can look a little bit messy. So what we can do instead is what's known as an early return. Essentially, we just say if the physics handle equals null pointer, you have to put a double equal sign here, otherwise it's an assignment. Then we can go down to do some braces, and we can just put a return in here. So what this is going to do is, if we've got a null pointer for the physics handle, it returns straight away and doesn't execute the rest of the function, thus making it safe in the rest of the function to use the physics handle as we wish. So we're going to do that. We're going to go down into where we have a hit. I think we don't need these log messages anymore, so I'm going to remove the else statement. I'm going to remove basically everything from the body of the if statement, and we're going to use our grabber. So we're going to do the physics handle, arrow, grab component at location with rotation. Then we have to provide it with a component we're trying to grab. If you have a look, the thing that it's expecting is a uPrimitive component. Let's see if we've got anything of the sort in our hit result. I'm just going to pop over to the documentation page for it and look for uPrimitive component. And you can see that get component would return the uPrimitive component that was hit. Perfect. That's just what we need. So we're going to look for the hit result dot get component. Going to give us what we want for the first argument. Now, next is an F name for a bone. Now, we don't actually want to grab anything by a particular bone. This would be the case if we had a skeletal mesh, but we don't. We have a static mesh. So we just use name underscore none. And generally speaking, with F names, where it's talking about bones, this comes up quite a lot. If you don't want to put anything in, you use name underscore none. Now we need the location that we're going to grab it at, and we've already said that we've looked into this. It's the hit result dot impact point. And then the rotation, well, the current rotation of that component will do, or the current rotation of the actor, whichever you prefer. So the hit result get component, we're going to grab that, hit result dot get component dot arrow, because it's a pointer, get component rotation. Like so. Now we can put the closing parenthesis on a separate line, and I'll put a semicolon there to finish off the statement. And that should be effective at grabbing our components. Now the next part of the puzzle is in tick component, where we want to again use the physics handle. So I'm going to copy the code for now, knowing that copying code to 3 places is a bit too many, and we might want to think about pulling it out into a function so that we reuse that. But in tick component, we're going to use the code for now to finish off the statement, and that should be effective at grabbing our components. Now, the next part of the puzzle is in tick component, where we want to again use the physics handle. So I'm going to copy the code for now, knowing that copying code to 3 places is a bit too many, and we might want to think about pulling it out into a function so that we reuse that. But in tick component, we're going to use the physics handle. We're going to early return if we can't get hold of a physics handle. And then what we're going to do is we're going to try and set that target location. So we're going to do physics handle arrow set target location and rotation. And let's have a little bit of a think about this. What kind of target location might we be interested in setting? Well, essentially it's going to be the same as we did with the endpoint. We're going to take our current location, then move it outwards in the forward direction by a certain distance. Now this will be configurable. You could use the max grab distance, but I find that in practice that feels too far away. So if we go to our grabber.h, we're going to create a new uProperty called edit anywhere, and it's going to be a float called the hold distance. And I'm going to set this to 200. grab a CPP, we can go into our tick function and try and create this target location. So it's going to be an F vector called target location. I'm going to set that equal to the get component location plus the get forward vector multiplied by the hold distance. So then we can use that as the target location. That's going to be our first argument. And then we need the target rotation. Well, for that, I'm just going to use the rotation of the current component so that as we look around, we're going to rotate the object with our view. So we can just do the get component rotation to get the rotation of the current grabber scene component. Now let's put a semicolon on the end of that line. And we compile and see how this works. Now after we've compiled successfully, let's select the gargoyle and just make sure that we change its mobility from static to movable, because we do need it to be able to move in response to physics. And let's make sure that it's simulating physics. Let's go to the physics category and check the simulate physics button. Let's hit play and try and pick it up. So nothing's happening at the moment, but it does seem to be stuck inside the floor, so that's not ideal. Let's try and lift it up a little bit so that it's not stuck inside the floor. Let it drop onto the floor like that. Now try and pick it up. It does seem to have got stuck inside the floor again, so let's just try a second time. Okay, so it's a little bit unreliable, and sometimes if you catch it straight away, it picks up the gargoyle just fine, and you can pick it up like that. I'm noticing the rotation isn't correct, and this is because I've used the wrong thing in the grabbing the physics component. I got the rotation of the gargoyle, and now we're trying to keep that rotation. What I actually needed to use was the rotation that we're using in tick, the rotation of the grabber. So let's go ahead and change that and recompile, and we'll just hit play again and try and grab it. There you go. This time I grabbed it and I got the correct rotation, the exact rotation that it had. And you can see that it does look like it's being grabbed on a spring. If I try and push it through a wall, it tries not to go through the wall as much as it can. It does eventually pop through the wall. Using it tick, the rotation of the grabber. So let's go ahead and change that and recompile, and we'll just hit play again and try and grab it. There you go. This time I grabbed it and I got the correct rotation, the exact rotation that it had. And you can see that it does look like it's being grabbed on a spring. If I try and push it through a wall, it tries not to go through the wall as much as it can. It does eventually pop through the wall. but it is trying to observe physics as I move it around. So I'd like to challenge you now to pull out a new function called getPhysicsHandle. It's going to be private. It should return a uPhysicsHandle component, and it should remove this duplicated code of needing to get the owner and find the component by class log, so that it shows up and we know that we've done something. Wrong. Pause the video and have a go. Okay, welcome back. First of all, we go to the header file where we're going to put this in the private. I'm going to have it cut it out of the grabber, so the include regarding the physics handle. We need to put it in the grabber.h, where we're going to put it above the generated.h. That's the last thing always in. Header files. And why do we not need to have it in the CPP as well? Well, because we're including grabber.h, so anything that we put in grabber.h will automatically be in the CPP. So we can put that include in there. Now we can go down to where we're defining this function and call it the getPhysicsHandle, pair of parentheses like that. And I think this should be const. It shouldn't change anything in our grabber to call this function. Let's go over to the CPP, go to the bottom where I'm going to paste in our definition. I'm going to stick a uGrabber : at the front. and then I'm removing the semicolon, adding a pair of braces. And what we want to do is take where we've got this get owner line, and we're just going to cut that out and replace it with get physics handle, like so. And then in the get physics handle, we can simply return the get. Owner, find component by class, etc. And now we can replace this also where we're doing it in tick component. We're getting hold of the physics handle. Let's replace that little bit of code with get physics handle. Now it's such a small piece of code, it's almost not worth it, but it's definitely worth it for the practice at this point and for the fact that we might add some log messages. Now in begin play we don't actually need to get the physics to handle at all, so I'm just going to remove that code there. But what I am going to do is I'm going to add a log message. So we're going to create a variable to store our result here, because if we return and then try to print a log message, that's not going to work. So we're going to have a uPhysics handle component called result. That's what we're going to return out of here. And we'll say if the result is equal to null pointer, well, then we need to ulog with a warning, or in fact an error really, and we're going to say grabber requires a uPhysics handle component. And then after the if statement, so this will happen whether or not it is null, we're going to return the result. So let's go ahead and compile that and check it all works. Seems to have succeeded. And then after the if statement, so this will happen whether or not it is null, we're going to return the result. So let's go ahead and compile that and check it all works. Seems to have succeeded, and I can see it must be working because when I left click in the scene, I'm getting the blue or debug orbs being drawn, and they wouldn't be drawn if we weren't getting hold of that physics handle component. Great stuff. So in this lecture we've been able to grab our gargoyle statue using our grabber, albeit sometimes it can be a little bit unreliable, and we're going to sort this out in upcoming lectures. So I'll see you there. Lecture we're going to be making the grabber much more reliable, and also we are going to be making it possible to drop a grabbed component so that we can throw it around and generally have it be a little bit more useful. Let's dive in and see how this is done. Now, the reason we're often not able to pick up this gargoyle is that components that are simulating physics for performance sake will go to sleep when they have been still for a certain amount of time. And that's what we're seeing. This gargoyle's physics simulation is going to sleep, and it's not being woken up when we attach to it with our physics handle. So what we need to learn to do is to wake it up when we hit it with a sphere trace. Now let's go and have a look at the uPrimitive component documentation. We've seen that the uPrimitive component is the thing returned by our hit result. But what actually is a primitive component? So it says it here in the documentation that a primitive component is a scene component that contains or generates some sort of geometry and is rendered or used as collision data. So generally speaking, primitive components are ones that can simulate physics. So we can expect to find some physics simulation methods on here. And what I'm going to look for is a function with the keyword wake in it. we're going to look through a few functions until we find one that says wake all rigid bodies. Rigid bodies are essentially a physics term for objects that simulate physics. So you can see it has a void return type, doesn't take any arguments. So we should be able to just call this when we are trying to attach to it. So if we go to our grabber CPP, inside our if statement, we've hit this component, we're about to grab it. The first thing we need to do is let's make a variable to store this U primitive component. So we'll have a U primitive component pointer called hit component. Set that equal to the hit result dot get component. And then using that hit component pointer, we can arrow wake all rigid bodies and then put the parentheses and a semicolon at the end. So this should just give that component a kick, wake it up so that it responds to the physics handle. Now let's replace where we've done hit result.get component in our physics handle call to grab component location, because we've now got a variable for that, and let's recompile. When that's done, let's go ahead and hit location, because we've now got a variable for that, and let's recompile. When that's done, let's go ahead and hit play and let the gargoyle sit a little bit on the floor for now and let it go to sleep, and then try picking it up, and you'll notice that we've got no problems picking it up, letting it lie on the floor, whatever. It's going to be fine and wake up those physics rigid bodies and start simulating them so that it can be lifted and grabbed. Now you may have noticed that we aren't currently able to release the physics handle, so that's going to be your challenge to do that in the release function. So you're going to call release component on that physics handle. That is a function that's available on the physics handle pointer. You're going to check first if we have a get grabbed component. So if you get grabbed component, it returns a pointer to the grabbed component. That pointer will be null if the physics handle isn't currently grabbing anything. So you can use that to check whether we've got anything and only release if we are currently grabbing something. And as a bonus, you can have a go to see if we can set the target again only if we are grabbing something. Pause the video and have a go. Okay, welcome back. So let's go over into grabber CPP. I'm going to go into the release function and remove the release log. And in here, we're going to put an if statement, and we're going to say if, and now we need to get hold of our physics handle. So we're going to, first of all, do a U physics handle component pointer, which we're going to call the physics handle, and set that equal to get physics handle. So then we're going to say if the physics handle is equal to null pointer, we want to go ahead and return, because we're not going to be able to do anything, release anything, if we don't have a physics handle at all. Then we want to check whether we are currently holding on to anything with our physics handle. So we can say if the physics handle arrow get grabbed component parentheses not equals null pointer, then inside the body of this if statement means we've got something currently grabbed. Well, then we're going to do a physics handle arrow release component, which is going to let it go, as the name would suggest. And one thing I didn't do in the code here, but it's probably worth adding to yours, is that before we release the component, it's worth going ahead and calling get grabbed component, and then adding the wake all rigid bodies, just like we did before we grabbed the component, because if we were to grab a component and not move around for a little while, it may also go to sleep, and so release. It would do nothing. nothing. So this is worth adding as it would catch that corner case. And we want to not set the target location in tick if we have got a physics handle that's not currently grabbing anything. So here in our tick components, we're going to put an if statement that's going to be exactly the same. It's going to be saying physics handle arrow get grabbed component not equal to null pointer. Then in the body of the if statement, we're going to put the calculation of the target location and the setting target location in that physics handle as well. Let's recompile and try this out. Let's go ahead and hit play and try and grab the gargoyle. And then if I let go of the mouse, it drops down to the floor again. So, and it seems, and hit location in that physics handle. Then in the body of the if statement, we're going to put the calculation of the target location and the setting target location in that physics handle as well. Let's recompile and try this out. Let's go ahead and hit play and try and grab the gargoyle. And then if I let go of the mouse, it drops down to the floor again. So, and it seems to not be affected by whether it's awake or asleep. We seem to be waking it up no matter whether every time we're picking it up essentially. So that seems to be working exactly as I'd like it to. It's not getting stuck, it's feeling just about right. The only weird thing slightly is when I move into it, you can see it does this weird jittering because it's actually colliding with the player. Now we can fix this just a little bit by going to our gargoyle in the details pane, selecting the all category, scrolling down to collision and looking at our custom collision preset. And down in the object responses, we'll see a bit more about this later on. There is a pawn object response. This basically says, should I collide with the pawn, or what should my response be to the pawn? Well, I'm going to set it to overlap with the pawn, and that means that if it collides with me, it essentially just ignores it. And then one more thing we have to do is, because this is actually made up of two static meshes, they've got their own collision set.